Hello there, and welcome to the calm space of Lumi-verse NL. Tonight, we drift into questions that have no answers, the quiet edges of what science still cannot explain. Even after centuries of discovery, the universe remains a vast, unsolved story. Each law we uncover opens another doorway. Each answer whispers another why. We can describe the movements of galaxies, the birth of stars, and the behavior of atoms, but not why there is anything here at all. Why does the universe exist? It is perhaps the simplest question a human can ask, and yet the hardest one to answer. Physics tells us how the universe behaves once it exists. Cosmology traces time back to the Big Bang, to that first luminous instant when everything began. But what came before that? Why should there be laws of nature at all? Laws capable of making a universe. That mystery sits at the foundation of all science. Quantum theory suggests that what we call nothing is not truly empty. Even in perfect vacuum, space itself trembles with fleeting particles, tiny sparks of being that flicker in and out of existence. Some scientists wonder if our entire universe may have arisen from such a fluctuation, as though nothingness itself could not remain still. Others imagine a multiverse, a boundless field of countless universes, each with its own laws, each blinking into being from the void. If that's true, then our question only deepens. Why does the multiverse itself exist? Why does reality refuse to be nothing at all? Philosophers sometimes suggest that existence may be the natural state, that nothingness cannot truly be. Maybe reality must exist in some form forever, but these are not ideas we can test. No telescope, no experiment, no collider can reach that far. Every atom in your body, every star in the night sky, every law that holds them together, all rest upon this one unanswerable truth, that something is here instead of nothing. It is the quietest, deepest mystery in science, and perhaps the oldest one ever asked. So as you listen, breathe softly and let your thoughts expand. You are part of this mystery, made of it, moving within it. Because to exist at all is already a miracle. The universe itself can't explain. In the beginning, there was light, but we still don't know what sparked it. Science calls it the Big Bang. The moment when space and time themselves unfolded from a single, unimaginable point. Nearly 14 billion years ago, the universe burst into being, expanding faster than light, filling the void with energy, matter, and possibility. Yet, the question remains, what caused it to begin at all? Cosmologists can trace the universe back to the first fractions of a second, to an era when everything was pure heat and density, a sea of particles colliding in chaos. Then, suddenly, something extraordinary happened. The universe swelled outward in an instant of cosmic inflation, stretching space itself beyond comprehension. But what triggered that expansion? Why did it start? And why did it stop? Some theories suggest that the Big Bang was not an explosion, but a transformation, a quantum fluctuation where reality itself folded open, giving rise to space, time, and energy in a single trembling breath. Others propose that our universe was born from the collapse of a previous one, that creation and destruction are part of an eternal cycle, universes expanding, fading, and beginning again. But perhaps the question of before makes no sense at all. If time itself was born with the Big Bang, then there was no before to speak of. only a timeless stillness giving way to motion. The origin of everything may lie beyond the reach of cause and effect. Our instruments, the Hubble telescope, the Planck satellite, and now the James Webb, can glimpse the afterglow of that first fire, the faint cosmic background still echoing through space. They show us how the universe cooled, how galaxies condensed from invisible mist, how the first light took form. But none can see the spark itself. We can measure expansion and calculate the universe's age. But the true first moment, the instant existence began, remains hidden in shadow. Maybe there was never a single beginning, but many, endlessly repeating across infinite realities. Or maybe there was one quiet spark, a whisper that became everything. As you listen, imagine that first flash of creation, a point of nothing turning into all that is. That light still travels across the sky tonight, faint but eternal. And somewhere within it, the mystery of beginnings continues to unfold. Time always moves forward, yet no one knows why. Every heartbeat, every drifting thought, is carried by a current we cannot see, a one-way stream that flows from what was toward what will be. We call it the arrow of time. It shapes everything we know. Stars burning, galaxies collapsing, lives beginning and ending. And yet, when we look into the equations that describe the universe, nothing demands that time must move in only one direction. At the deepest level, the laws of physics are symmetrical. They work just as well forward as they do backward. A planet's orbit could be reversed, a collision rewound, and the mathematics would remain perfectly valid. But reality refuses to behave that way. We remember the past, never the future. Broken glass does not leap back together. A flame once extinguished never reforms in mid-air. Entropy, the slow slide toward disorder, gives time its direction. As the universe expands, energy spreads, order decays, and structures dissolve. Physicists say the cosmos began in an exceptionally ordered state, a smooth, uniform sea of energy so low in entropy that time itself could begin to flow. But why would the universe start that way? Why should the initial conditions be so improbably tidy, when chaos is the natural tendency of things? Some believe the arrow of time is tied to this original asymmetry, a whisper from the birth of the cosmos that still guides every second today. Others propose that time's direction emerges from information, that as particles interact, they create records, and those records give meaning to the idea of past. When information is lost, as in black holes, the very concept of time becomes uncertain. Perhaps the flow of time is not a cosmic law at all, but a reflection of how we, as conscious beings, process change. Our brains are wired to perceive sequence, to turn moments into stories, memories into meaning. The sensation of time passing may be the universe observing itself, each awareness a tiny clock counting its own existence. If that's true, then time is not something we move through. It is something that unfolds within us. Still, the mystery deepens. If the Big Bang set the arrow in motion, what happens when the universe reaches its end? If everything dissolves into uniform heat, if every star fades and every atom cools, does time itself stop, or does it continue? An endless silence, stretching forever into darkness. Even now, cosmologists wonder if time might flow differently in other realms, in black holes, near the speed of light, or across quantum boundaries, where cause and effect blur together, In such places, the past and future might intertwine, coexisting like reflections on the surface of still water. Perhaps time is not linear at all. Perhaps it loops, or folds, or branches into countless threads, each moment giving rise to another universe, every choice, every possibility, expanding outward like ripples in infinity. If so, the arrow of time we feel may be just one direction among many, one narrow path through a much larger reality. And yet, in this moment, sitting beneath the quiet rhythm of your own heartbeat, you can feel its pull, the gentle drift of seconds passing by. The universe expands, stars burn, atoms cool, and you breathe, all of it happening only once, never to repeat. That is the true wonder of time. It carries us forward, whether we understand it or not. So as you rest, let time move softly through you. Let the seconds stretch like starlight fading across the dark. There is no need to chase the future, for you are already flowing within it. And somewhere, between one heartbeat and the next, you may sense what scientists have yet to prove, that time itself is both mystery and melody, a song the universe keeps singing even when no one knows the words. Most of the universe is made of something we cannot see. When astronomers observe galaxies spinning through the darkness, they find stars moving too quickly, far faster than the visible mass of the galaxy should allow. By every known law of gravity, those stars should have flown apart long ago, scattered into the void, and yet they remain bound, circling quietly in patterns that defy logic. This invisible glue, this unseen mass, has come to be known as dark matter. It does not emit light, does not absorb it, does not reflect it. To our eyes, to our telescopes, it is utterly transparent, and still, its gravity holds galaxies together, bends the paths of distant starlight, and leaves faint fingerprints in the cosmic web that spans the universe. When scientists map the distribution of matter across space, they find a pattern: clusters of galaxies connected by filaments and separated by vast, empty voids. The visible galaxies are only the glowing tips of an iceberg, while beneath them lies a hidden ocean of dark matter, 5 times more abundant than everything we can see. Without it, the universe would be unrecognizable, a thin mist of drifting stars, unable to form into galaxies or planets. But what is it, really? For decades, physicists have searched for the true nature of dark matter. Some suspect it is made of exotic particles that barely interact with ordinary matter, known as WIMPs, weakly interacting massive particles. Others imagine lighter, more ghostly forms, like axions, particles that slip through detectors as though they were not there at all. Some even suggest that dark matter could be an illusion, that our understanding of gravity itself might need to be rewritten. To find it, experiments have been buried deep beneath mountains and ice. Detectors the size of cathedrals sit in absolute silence, waiting for a single dark matter particle to collide with an atom. So far, none have. The results come back empty, as though the universe is playing a quiet game of hide and seek with its own foundation. And yet, the evidence is undeniable. We see dark matter not directly, but through its pull. It sculpts the shapes of galaxies, draws filaments of cosmic structure across billions of light years, and subtly tugs on every ray of light that crosses its path. Even the cosmic microwave background, the afterglow of the Big Bang, bears the faint imprint of its presence, ripples frozen into the earliest fabric of space. In the heart of clusters, Astronomers watch galaxies behaving as though embedded in a massive, invisible halo. Gravitational lensing, the bending of light by unseen mass, reveals ghostly outlines of something that cannot be touched. We can measure its effects precisely, but not the thing itself. Like wind shaping the dunes of a cosmic desert, dark matter moves unseen, but leaves a perfect record of its passing. What makes the mystery so haunting is that every atom of our bodies, every planet, every shining star belongs to the minority. We are made of the rare, luminous dust that floats within a much larger, darker sea. Almost all the matter in existence is invisible, silent, and unknown. It surrounds us, passes through us, and yet we cannot feel it. Maybe dark matter is not separate from us at all, but another aspect of the same universe. A hidden harmony vibrating at a frequency our senses cannot perceive. If one day we finally detect it, perhaps we will find that it was always close, woven through every heartbeat, every atom, every breath of the cosmos. Until then, we drift inside a mystery that defines everything we see. The galaxies turn, the stars orbit, and the universe holds together under the weight of an invisible hand. We cannot touch it, we cannot see it, and yet it carries us. An unseen presence, the dark thread holding the tapestry of creation in place. There is an invisible force that stretches the universe apart, faster and faster, farther and farther, and no one knows what it is. Astronomers once believed that cosmic expansion, set in motion by the Big Bang, would eventually slow down. After all, gravity should be pulling everything back together, drawing galaxies inward like the tide. But when scientists looked deeper into the night, studying the light of distant supernovae, they found something that shattered expectation. The universe is not slowing down at all. It's accelerating. This discovery, made in the late 1990 seconds, changed everything. It suggested that some unknown energy is embedded within space itself. A silent pressure that pushes outward, overwhelming gravity on the grandest scales. Physicists gave it a name: dark energy. But the name is a placeholder, a label for something we do not understand. It makes up roughly 70% of the entire cosmos, and yet we cannot see it, touch it, or measure it directly. One theory proposes that dark energy is the energy of empty space, a constant property of the vacuum. Even in the absence of matter, space may hum with a background field, a subtle force woven into the geometry of existence. This idea, known as the cosmological constant, was first introduced by Einstein himself. He called it his greatest mistake. But decades later, it returned as one of science's greatest necessities. Without it, the accelerating expansion makes no sense. Other scientists believe dark energy may not be constant at all, that it could evolve over time, changing in strength as the universe ages. If that's true, then the cosmos is not only expanding but transforming, its very laws shifting like a living organism adapting to its own scale. Still others wonder if dark energy isn't a separate force at all, but a sign that our understanding of gravity is incomplete. Maybe, on the largest cosmic distances, gravity behaves differently than the equations we've trusted for centuries. The mystery deepens when we imagine the universe's future. If dark energy remains steady, galaxies will drift farther apart, stars will burn out, and the night sky will fade until even the nearest galaxies vanish beyond view. The universe will stretch into a cold, endless darkness, a final silence called the heat death. But if dark energy grows stronger over time, the outcome is even stranger. Galaxies, stars, planets, even atoms themselves could be torn apart in what scientists call the Big Rip, a universe unmade by the same force that caused it to expand. We can measure its fingerprints everywhere, in the way galaxies scatter, in the faint glow of ancient radiation, in the expansion rate of space that increases ever so slightly each billion years. But we cannot see its face. Dark energy hides behind the fabric of reality, an invisible wind inflating space itself. Perhaps it has been there since the very beginning, a balance to the pull of matter and the whisper of gravity. Or perhaps it is new, a property emerging only after the universe grew vast enough to notice its own emptiness. If the cosmos is an ocean, then dark energy is the tide beneath it, slow, steady, and irresistible. Some physicists dream of uniting dark energy with dark matter, two invisible phenomena that shape everything yet refuse to reveal themselves. Maybe they are different expressions of one underlying truth, a deeper field connecting all existence, a theory waiting to be discovered, humming quietly beneath equations we have not yet learned to read. What makes the mystery so haunting is its consequence. Dark energy doesn't just shape the universe, it decides its fate. Every galaxy, every planet, every living being is adrift on that invisible current, sailing into an ever-widening night. And yet, there is something strangely peaceful about it, an unseen force expanding the canvas of creation, reminding us that the cosmos is not static, but alive, still unfolding, still changing, still carrying us into the unknown. So when you look up at the stars tonight, remember that the darkness between them is not empty. It is full of motion, full of energy, full of questions. The space that seems still is expanding even now, and somewhere in that silent acceleration is the pulse of a mystery that holds the future of everything. The universe seems perfectly balanced, almost impossibly so. Every law of physics, every constant, every interaction between particles appears tuned with exquisite precision to allow stars, planets, and life itself to exist. Change the strength of gravity by the smallest fraction, and the cosmos would collapse into black holes or drift apart into darkness. Alter the electromagnetic force by a breath, and atoms would never hold together. Even the tiniest adjustment in nature's constants would make life, and perhaps the universe itself, impossible. Scientists call this puzzle the fine-tuning problem. It is one of the deepest mysteries in all of physics. Why should the laws of nature take exactly the values they do? There is no mathematical reason for gravity, electromagnetism, or the strong and weak nuclear forces to have the specific strengths they possess. And yet, if they were even slightly different, hydrogen might not fuse into helium, stars could never shine, and chemistry, the foundation of biology, could not exist. It is as though the universe were set upon a knife's edge, balanced so precisely that it can sustain the complexity we call life. For some, this delicate order suggests coincidence, a cosmic accident among countless possibilities. For others, it feels like a sign of deeper design, a hidden principle guiding the equations of reality. One idea points toward the multiverse, a vast landscape of universes, each with different laws of physics. In that view, ours is not special because it was chosen, but because it is one of the few where observers like us could exist to notice it. A cosmic lottery win, written into probability itself. But if there are countless universes, each sealed from the next, we may never be able to test the idea. The evidence would remain forever beyond our horizon. Another possibility is that a deeper, undiscovered law determines everything. A principle that fixes the constants the way geometry dictates the shape of a sphere. Perhaps these numbers could not be any other way. Maybe the laws of nature are inevitable, emerging from the logic of mathematics itself, as though reality were solving its own equation. Still, there is something almost poetic about the way everything fits together. From the pull of gravity that forms galaxies, to the delicate balance of nuclear forces that forge carbon in stars, and to the transparency of water that lets light reach the oceans. Each detail seems improbably kind to life. Even the tiny asymmetry that allowed matter to triumph over antimatter was exactly what it needed to be. Not too large, not too small. It's easy to forget how precarious our existence is. The air we breathe, the warmth of the sun, the chemistry of our cells, all depend on cosmic coincidences, woven through time since the universe began. If the fine-tuning of the cosmos were written as music, it would be a harmony of impossible precision, a symphony of constants playing perfectly in tune. Yet science does not settle for poetry alone. Physicists continue to seek a framework that explains this balance, without invoking luck or design. Theories like string theory hint that all forces and particles might emerge from a single underlying vibration, that the tuning is built into the structure of existence itself. But without evidence, it remains a dream, a whisper of order beneath the noise of reality. Some thinkers suggest another angle entirely. Perhaps we see fine-tuning only because we are here to see it. If the universe were sterile, there would be no eyes to observe its emptiness. Our presence, then, becomes part of the equation. We are not separate from the balance, we are the balance, the living expression of the universe's precision. No matter which idea proves true, fine-tuning reminds us how improbable it is to simply exist. Out of infinite possibilities, we inhabit one reality, where the constants align just right for consciousness to arise and wonder why. That we can even ask this question may be the most finely tuned mystery of all. So tonight, as you drift between thought and sleep, remember that you are part of this delicate balance. Your heartbeat, your breath, your very atoms are tuned to the same laws that shaped galaxies and stars. The universe did not have to be this way, and yet, somehow, it is. A perfect alignment between chaos and order, between nothing and everything. And in that fragile harmony, life found its place. No one knows how large the universe truly is, or if it ever ends. What we can see is only a small, glowing island in a vast cosmic sea. Astronomers call it the observable universe, a sphere nearly 90 billion light-years across, filled with galaxies, stars, and light that has been traveling toward us since the beginning of time. Beyond that horizon lies everything we cannot see, a silent expanse that may stretch forever. The limit is not a wall, not a physical boundary, but the edge of what light has had time to reach us. The universe is about 13.8 billion years old, so light from anything farther away hasn't yet arrived. It is as though we stand inside a bubble of visibility, surrounded by an infinite night that remains beyond reach. But what lies outside that cosmic horizon? More galaxies, other realms, perhaps something stranger, remains unknown. One possibility is that the universe is truly infinite, stretching endlessly in all directions, with no center, no edge, and no border. In such a universe, space would contain uncountable galaxies, endless worlds, and perhaps endless versions of ourselves. each born from the same physical laws repeating across infinity. But infinity is difficult to grasp and even harder to test. If the cosmos has no edge, then the question of how large becomes meaningless. Another idea is that the universe is finite but unbounded, like the surface of a sphere. Travel far enough in one direction, and you could, in theory, return to your starting point, just as a traveler sailing around the Earth finds the same horizon again. In this view, space wraps back on itself, a self-contained loop without borders or ends. You could journey forever without ever crossing an edge, because there is no edge to cross. To search for clues, cosmologists study the cosmic microwave background, the faint afterglow of the Big Bang. Its ripples, frozen in light, carry information about the shape and curvature of space. If the universe were strongly curved, those patterns would show it. So far, the evidence suggests that the universe is remarkably flat, but flat does not necessarily mean infinite. It could simply be very, very large, curved so gently that we cannot yet detect it. Still, the idea of boundaries lingers. Does space simply go on forever? Or is there a limit beyond which physics itself changes? Perhaps there are regions of the cosmos we will never see, pockets sealed off by the speed of light and the expansion of space. Even now, galaxies at the farthest reaches are receding faster than light can travel. Their light will never reach us. In a sense, they already belong to a future universe. We can only imagine. What's even more haunting is that the further we look, the younger the universe appears. Each distant galaxy is a time capsule showing us the cosmos as it was billions of years ago. When we peer across space, we are also looking into the past, into eras when the first stars were still forming, when the universe itself was young. Beyond that lies a darkness no telescope can penetrate, a frontier where the very concept of distance loses meaning. Perhaps there is more beyond the visible horizon, more space, more time, more universes, budding like bubbles in an infinite sea. Or perhaps everything we will ever know is contained here, in this luminous island of existence surrounded by mystery. Either way, what we see is not all that is. The cosmos is larger, older, and deeper than our minds can hold. Every night sky, every distant light is only a glimpse, a fragment of an endless whole. And yet, fragment is enough to remind us how small we are and how vast the universe must be. So, as you lie beneath the stars, imagine the horizon of the observable universe, a glowing bubble of time expanding outward at the speed of light. Beyond it lies silence, an infinite distance filled with questions, and within it, tiny observers looking out from our small corner of forever, wondering if infinity ever ends. What if our universe is not the only one? What if everything we know, all the galaxies, all the stars, every atom, and every thought, is just one bubble in an infinite cosmic sea? This is the idea of the multiverse, one of the most daring and unsettling possibilities in modern science. It suggests that our universe may be only one of countless others, each with its own laws of physics, its own constants, its own version of reality. In some of these universes, gravity could be stronger, that light could travel differently, or time itself might flow in another direction. There could be worlds where stars never form, and others where life evolves under alien skies. There might even be universes that look almost identical to ours. Copies so similar that another version of you is out there right now, wondering the same things, asking the same questions, perhaps even listening to this very thought. The multiverse first emerged as a natural outcome of inflation, the theory that the universe expanded faster than light in the first fraction of a second after the Big Bang. According to this idea, inflation might not have happened just once, but continues endlessly, bubbling new universes into existence like foam on an infinite ocean. Each bubble becomes a separate universe, sealed off from the others by vast distances and expanding space. We live in one of them, a quiet island in a sea of countless worlds. String theory. Another powerful framework of physics also hints at a multiverse. Its equations allow for many possible configurations of physical laws, each describing a different kind of universe. In this grand landscape, our cosmos could be just one tiny valley within an unimaginable terrain of possibilities. If true, the constants we see, the charge of the electron, the strength of gravity, the speed of light, may simply be local conditions, not universal truths, but properties of our particular cosmic neighborhood. And yet, this idea raises a paradox. If other universes exist beyond our cosmic horizon, how could we ever know? No light or signal could travel between them. No experiment could reach across that boundary. By definition, the multiverse might lie forever beyond observation. It stretches the definition of science itself. For how can we test what we can never touch? Still, clues may exist, hidden in the patterns of our own universe. Some physicists search the cosmic microwave background for faint imprints, bruises, where another universe may have brushed ours long ago. Others look for unusual alignments in the large-scale structure of galaxies, subtle fingerprints of a deeper reality beyond our own. So far, the evidence is inconclusive, a silence across the void. But silence does not mean absence. It only means the answer is waiting. If the multiverse is real, then the mystery of fine-tuning may find its resolution. We exist in a universe that allows life because only such universes can give rise to beings capable of asking questions at all. It's not that our cosmos was designed for us. It's that countless universes exist, and we happen to live in one of the rare ones where the music of physics plays in harmony with life. Philosophically, the multiverse changes everything. It redefines uniqueness. It humbles the idea of everything, because everything might just be one small part of something larger, something endless. And it invites a strange comfort. If other universes exist, perhaps nothing is ever truly lost. Perhaps every possibility, every story, every dream imagined and forgotten finds its home somewhere in that vast expanse of reality. Whether or not the multiverse is true, it reminds us of a profound truth. Our imagination is itself a kind of universe, a place where possibilities multiply without limit. Science, like the cosmos, expands through curiosity, each question birthing 1,000 more. And as we drift beneath the stars, it's worth remembering that we might not be staring into one universe, but into infinity, an endless ocean of creation where each world is a reflection of another, and every mystery opens the door to countless more. Space and time, the stage on which all of existence unfolds, may not be what they seem. Einstein showed that they are not rigid or separate, but woven together into a single fabric called space-time. Gravity, in this view, is not a force pulling objects together, but the bending of that fabric caused by mass and energy. Planets orbit stars not because they are drawn by invisible strings, but because they follow the natural curves of space itself. It is a beautiful, elegant idea, and one of the most successful theories ever conceived. But when we look deeper, the picture begins to unravel. At the smallest scales, where quantum mechanics governs, space-time no longer behaves like a smooth surface. Instead, it flickers and foams with uncertainty, bubbling with virtual particles that appear and vanish in a heartbeat. Quantum theory and general relativity, the two great pillars of modern physics, describe completely different worlds. And yet both must be true, for the universe contains both the very large and the very small. But when we try to make them work together, the equations collapse. Infinity rises from the math like a wave, and all consistency dissolves into chaos. This conflict, the gap between gravity and quantum theory, is one of the greatest mysteries in science. How can space and time be smooth and continuous in one theory, yet grainy and uncertain in another? Physicists have spent decades searching for the bridge between them, a theory of quantum gravity that would explain how space-time behaves at the deepest level. Some suggest that space-time itself may not be fundamental at all, that it is an emergent property, a pattern that arises from something more basic, just as temperature emerges from the motion of countless molecules. In this picture, space and time are like a mirage, irreal to our perception, but built from an underlying network of information or energy. Quantum entanglement, where two particles remain linked across vast distances, may hold the clue. Perhaps space-time is woven from those invisible connections, a web of relationships, not a stage, and reality itself is built from information. If that is true, then the universe might not be a continuous fabric at all, but a vast lattice of interacting data, pixels of existence, so small and subtle that we can only glimpse their effects indirectly. Every point in space would be connected to every other through threads of quantum communication. In such a universe, gravity, matter, and even the flow of time would all emerge from how information is shared across this invisible network. Others take the mystery further. They ask if time itself is even real, or merely an illusion created by our limited perception. Perhaps the universe is timeless, a single, complete structure where past, present, and future coexist as different slices of one grand reality. We experience time because we move through that structure, frame by frame, like a consciousness reading its own existence one moment at a time. Still, we cling to the sensation of movement, the unfolding of events, the ticking of clocks, the aging of stars. Our lives depend on time's rhythm, and yet science whispers that it might be an illusion, that everything which ever was, or ever will be, already exists in the fabric of the cosmos. In that sense, we do not travel through time. We are time, expressions of change within the larger geometry of being. What lies beneath space-time remains hidden from our instruments, buried beneath scales far smaller than we can probe. The Planck length, a distance 100 billion times smaller than an atom, marks the boundary beyond which the smooth surface of reality may dissolve into something unrecognizable. At that scale, space might churn like a quantum ocean, filled with loops and threads that give birth to the shape of everything. We have mathematical glimpses of these possibilities: string theory, loop quantum gravity, holographic models, each painting part of the picture, but none complete. It is as if nature hides her foundation beneath layers of mystery, revealing only what we are ready to understand. And yet, even in uncertainty, there is beauty. The idea that space and time could arise from something deeper reminds us that reality is not static. It evolves, adapts, and perhaps even dreams itself into being. We live not in space-time, but as part of it, ripples in a fabric that may itself be alive with information. So the next time you look at the stars, remember that the distance between you and them is not empty. It is filled with the invisible structure of the universe, a silent architecture that holds everything together, from the smallest particle to the farthest galaxy. And somewhere within that structure, between gravity and quantum uncertainty, lies the secret language of reality itself, a code still waiting to be read. At the smallest scales of reality, something extraordinary happens. The rules of the everyday world no longer apply. Objects blur into waves, positions dissolve into probabilities, and certainty itself disappears. This is the strange domain of quantum mechanics, the framework that governs everything from atoms to light itself. It works with perfect precision, predicting results to many decimal places, yet its meaning remains deeply mysterious. In the quantum world, a single particle can exist in multiple states at once, a phenomenon called superposition. An electron is not here or there, but both until someone observes it. It behaves as if it travels through two paths at the same time, interfering with itself like a ripple crossing its own reflection. Only when we measure it does it choose a definite outcome. Before that moment, reality exists only as possibility, a cloud of potential waiting to take form. The famous double-slit experiment makes this visible. When particles such as electrons are fired through two narrow openings, they form an interference pattern, a wave-like design of light and shadow, even if sent one at a time. It's as though each particle passes through both slits simultaneously, aware of all the paths it could take. But when we observe which slit it goes through, the pattern vanishes. The act of observation changes what happens. The particle behaves differently simply because we are watching. This raises one of the most haunting questions in physics. What does it mean to observe something? Does consciousness play a role, or does measurement itself collapse the wave of possibilities? In the traditional interpretation, the wave function, the mathematical expression of all potential outcomes, collapses into one reality when observed. But no one agrees on what exactly causes that collapse. Some scientists believe every possibility happens somewhere. When a quantum event occurs, the universe splits into multiple versions, each carrying out one possible outcome. In one universe, the particle goes left. In another, it goes right. This is the many worlds interpretation, a breathtaking idea that turns every quantum event into a branching of infinite realities. If true, then every choice, every flicker of randomness spawns a new universe, a limitless forest of possibilities, all real, all existing in parallel. Others see superposition as a reflection of our ignorance, not a physical overlap, but a mathematical description of what we simply do not yet know. In that case, reality is definite, and it is only our measurement that reveals which part we are able to see. But even this interpretation struggles to explain why the act of observation itself should cause the wave of probability to shrink into a single line of truth. Experiments keep deepening the mystery. Physicists have created quantum states, involving not just individual particles, but entire molecules containing thousands of atoms, objects large enough to be seen with advanced instruments, and yet still capable of being in two states at once. How can something so tangible behave like both matter and energy, both here and not here at the same time? At the heart of the paradox lies the question of reality itself. Is the universe fundamentally deterministic, unfolding with perfect order beneath the surface of randomness? Or is indeterminacy true unpredictability, woven into the fabric of existence? If reality only becomes real when measured, then what is it doing the rest of the time? Does the moon exist when no one looks at it? Einstein famously refused to believe that the universe could be built on chance, insisting that but every experiment so far seems to say otherwise. The quantum world feels like a cosmic riddle, a place where particles dance to rhythms that only probability can describe. And yet, this same uncertainty underlies everything we touch. Your body, your breath, the light entering your eyes, all emerge from the same quantum fields that defy understanding. The world you experience as solid and certain is built upon a foundation of shimmering possibility. Perhaps the strangest part of all is that quantum mechanics works. It has given us lasers, computers, MRI machines, and every modern technology that defines civilization, all built on equations that even Einstein found unsettling. The theory is complete in its predictions, but incomplete in its meaning. It tells us how the universe behaves, but not what that behavior means. So tonight, imagine a single particle drifting, splitting, overlapping with itself. It exists everywhere it could possibly be until it meets your gaze, and then it chooses. Reality solidifies for a heartbeat, only to dissolve again into waves of possibility. In that moment, you and the universe are partners in creation, observer and observed, forever linked in the act of being. Gravity is the oldest of all the forces, and the weakest. It sculpts galaxies, holds planets in orbit, and binds the universe together with invisible hands. Yet, compared to the other fundamental forces of nature, it is astonishingly feeble. A small refrigerator magnet can lift a paperclip against the pull of the entire Earth. Why should the force that rules the cosmos be so fragile on the smallest scales? This question is known as the hierarchy problem, and it remains one of the greatest mysteries in modern physics. The strong nuclear force glues the atomic nucleus together. The electromagnetic force shapes chemistry and light. The weak force governs radioactive decay. Each of them is billions of times stronger than gravity. And yet, gravity dominates the universe. It shapes the stars, bends space, and dictates cosmic destiny. How can something so weak rule everything? Some physicists suspect that gravity's apparent weakness is an illusion. Perhaps it is not truly feeble, but spread out, diluted through hidden dimensions of space. In certain theories inspired by string theory, the universe may contain additional dimensions, folded up so tightly that we cannot perceive them. If gravity extends into these hidden realms, then only a fraction of its strength would remain in our visible world. What we feel as weakness may be the echo of a much more powerful force operating elsewhere. Others propose that gravity might emerge from something deeper, not as a fundamental force at all, but as a side effect, a kind of statistical result arising from information and entropy. In that view, gravity is not pulling objects together, but the universe adjusting itself toward equilibrium. The curvature of space-time, the motion of planets, the fall of an apple, all could be the surface manifestation of hidden thermodynamic principles written in the fabric of reality. It is a strange thought that the weight we feel pressing us to the ground is not a true pull at all, but the universe balancing its own equations. Still, it fits with a deeper theme in science. The closer we look, the more we find that simplicity hides beneath complexity. The same mathematics that describe heat and disorder might also describe the bending of space-time around stars. Then there are theories that reimagine gravity altogether. Modified gravity models, quantum gravity, even emergent holographic theories, all attempt to rewrite the rules. In some, gravity weakens not because of hidden dimensions, but because its quantum carrier, the hypothetical graviton, interacts differently from other particles. In others, the strength of gravity may vary across scales, rising in the early universe and fading as the cosmos expands. Each idea fits part of the puzzle, but none explains the whole. What makes the mystery more profound is that gravity is the only force we cannot yet unite with quantum mechanics. Electromagnetism and the nuclear forces fit comfortably within the quantum framework, but gravity resists. When we try to quantize it, the equations collapse into infinities. It is as though gravity operates by its own language, a dialect of space-time that no other force can speak. And yet, gravity remains the most essential feature of our existence. Without its weakness, the universe as we know it could not exist. If gravity were slightly stronger, stars would burn out too quickly, collapsing into black holes before planets could form. If it were weaker, matter would drift apart, and galaxies would never take shape. Its frailty is not a flaw, it is a gift of balance, a fine-tuned whisper that allows the cosmos to endure. It is possible that gravity's secret lies in the interplay between space, time, and information, a hidden harmony connecting all other forces. Perhaps it is not a separate phenomenon at all, but the geometry of existence itself, a curvature not only of space, but of meaning. We walk every day within that mystery. We feel it as weight, but it is also the quiet hum of the universe, holding us close. The same force that keeps our feet on the ground, binds galaxies into clusters, and bends the paths of starlight across billions of years. It is both intimate and infinite. So when you drop a stone and watch it fall, remember that you are witnessing the dialogue between matter and space, the way the universe speaks to itself through curvature and motion. Gravity may be the weakest of all forces, but it is also the gentlest expression of connection. It is the thread that ties the stars together, the whisper that gives weight to being, and perhaps the quiet reminder can hold an entire universe in its embrace. Two of the most successful theories in human history describe our universe perfectly, and yet they cannot coexist. One governs the vast and the heavy. Einstein's general relativity, the theory of gravity and space-time. The other rules the small and the strange. Quantum mechanics, the theory of particles and uncertainty. Each has passed every test we can devise. Each predicts the behavior of the cosmos with astonishing precision. And yet, when we try to combine them, they collapse into chaos. This is the central paradox of modern physics, the divide between the smooth, continuous fabric of space-time and the jittering, probabilistic world of the quantum. Relativity tells us that gravity curves space and time, and that massive bodies like stars and black holes shape the geometry around them. Quantum mechanics tells us that everything, even light and matter, comes in discrete quanta packets of energy that behave unpredictably. When we bring these two realities together, their equations explode into infinities that make no physical sense. Inside a black hole, this conflict becomes unavoidable. Relativity predicts a singularity, a point of infinite density, where space and time collapse. But quantum theory forbids infinities. It demands that something deeper must happen, something that replaces that impossible point, with a new kind of physics we do not yet understand. At the edges of the known universe, in the first moments after the Big Bang, the same battle rages between these two descriptions of reality. For decades, physicists have searched for a single framework that unites the large and the small, a theory of everything. Such a theory would explain gravity as just another aspect of the quantum world, perhaps emerging from the same fundamental rules that govern all matter and energy. It would reveal what happens inside black holes, why space-time bends, and how the universe itself began. One leading candidate is string theory. It proposes that all particles are not points, but tiny vibrating strings of energy. Different vibrations produce different particles, like musical notes played on a cosmic instrument. In this vision, gravity, electromagnetism, and all other forces are simply harmonies in the same underlying melody. The mathematics is beautiful, but untested. The strings it describes are far too small to detect directly, 100 billion times smaller than a proton. Another approach, called loop quantum gravity, tries to quantize space-time itself. It imagines the fabric of the universe as a web of loops, tiny, discrete units that form geometry at the smallest scale. Space, in this theory, is not continuous, but pixelated, a shimmering lattice where distances and areas come in tiny quanta. If correct, this would mean that the smoothness of space is only an illusion, an average over countless microscopic threads of geometry. Both theories across the gulf between Einstein and quantum physics. None have yet succeeded completely. Our most advanced instruments, particle colliders, telescopes, and detectors, can test parts of the story, but the true meeting place of these two realms exists at energies and scales far beyond what we can reach. And so, the universe keeps its deepest secret. Two masterpieces of human thought describe it perfectly until they meet. Then, everything breaks. It is as if reality has built two separate languages, one for the cosmos above and one for the atoms within, and neither can fully translate the other. Perhaps the unification we seek is not mathematical alone. Maybe the separation itself is an illusion, a sign that space, time, are all faces of a single, unseen entity, a deeper layer of reality, where gravity and quantum mechanics are not rivals but reflections. Just as light can behave as both wave and particle, perhaps the universe can be both continuous and discrete, depending on how we look. Until we find that connection, we live in a divided world, one where the equations of Einstein and the equations of quantum theory each describe half of the truth. Between them lies a silence filled with infinite possibilities, waiting for a new language, one that can sing both the song of space-time and the whisper of the quantum. Somewhere in that silence, hidden beneath the mathematics, may lie the answer to everything. Not two theories at odds, but one universe, finally understood as a single thought. Deep in the heart of the universe, there are places where gravity wins, where the pull of matter grows so strong that nothing, not even light, can escape. These are black holes, regions of space where the known laws of physics break down. They are the strangest objects we know, and perhaps the purest expression of mystery itself. A black hole begins with collapse. When a massive star runs out of fuel, it can no longer resist its own gravity. The core implodes, shrinking smaller and smaller until all of its mass is compressed into a single, infinitely dense point, a singularity. Around this point lies the event horizon, the boundary beyond which nothing can return. To cross it is to vanish from the universe, as though reality itself ends there. Einstein's equations predict these objects perfectly. We can describe their gravity, their rotation, their effect on nearby stars and light. But they also lead us to paradox, because inside a black hole, space and time trade places. The future pulls inward, and all paths lead inevitably toward the singularity. There, density becomes infinite, and our mathematics, our understanding, ceases to make sense. Physicists suspect that this infinity is not a real place, but a sign that our current theories are incomplete. Quantum mechanics, which governs the small, and general relativity, which rules the large, both fail inside a black hole. Something new must take over, a theory of quantum gravity that does not yet exist. Whatever it is, it must explain what truly happens to matter and information that fall beyond the horizon. This leads to one of science's most enduring riddles, the information paradox. According to quantum theory, information can never be destroyed. But when something falls into a black hole, it seems to vanish forever. Even when black holes evaporate over unimaginable timescales, through a faint glow called Hawking radiation, no trace of what went in appears to return. If the information is lost, quantum mechanics breaks. If it somehow escapes, we must rewrite our understanding of space and time. Stephen Hawking's discovery of black hole radiation changed how we think about these cosmic abysses. It suggested that black holes are not eternal graves, but slowly evaporating objects, bleeding energy back into the universe over trillions of years. Yet the mechanism behind that process remains unknown. Does the information hide within the radiation itself, encoded in patterns too subtle to detect? Or does it live on the event horizon, imprinted across the surface like data on a cosmic hologram? Some physicists now believe that the entire universe may operate in this way, as a hologram, where all that we perceive in 3 dimensions is a projection of information stored on a distant surface. If that is true, then the inside of a black hole is not truly gone, but transformed. Its story written across the edges of reality. The horizon becomes more than a boundary. It becomes a mirror. Each photon, each particle, each piece of falling matter etched into the cosmic memory of the whole itself. Nothing truly disappears, it only changes form. But even this vision leaves deeper questions. What lies inside the singularity? Is there a bridge to another region of space-time? A wormhole, a tunnel leading elsewhere? Some mathematical solutions to Einstein's equations suggest it could be so, that black holes may connect to white holes, regions where matter is expelled rather than consumed. If such passages exist, they could link distant corners of the cosmos, or even other universes beyond our own. Yet no traveler could ever return to tell us. We have seen black holes indirectly for decades, through their gravitational pull, through the dance of stars that orbit invisible centers, through the X-rays emitted by matter spiraling toward the void. But in 2019, for the first time, humanity saw one. The shadow of a black hole in the galaxy M87, captured by the Event Horizon Telescope. It was not light that we saw, but the absence of it. a glowing ring around a darkness so absolute that it seemed to swallow even meaning. That image was a moment of awe, a reminder that the universe still hides secrets vast enough to humble us. Every black hole is both an ending and a beginning, a place where matter dies and mystery begins. They are the graveyards of stars, but perhaps also the seeds of new realities. When we gaze into them, we look into the limits of knowledge itself, a horizon beyond which lie answers we are not yet ready to see. And somewhere out there, in the heart of galaxies, billions of black holes spin silently, guardians of the unknown, reminders that even light must sometimes surrender to darkness. But maybe, just maybe, darkness is not the end at all. It could be the doorway to everything yet to come. Before galaxies and planets, before life or light, there was darkness. The early universe was a quiet ocean of hydrogen and helium, a fog so dense that no starlight could pass through. For hundreds of millions of years after the Big Bang, the cosmos existed in shadow, silent, cooling, and waiting. And then, something happened that changed everything. The first stars were born. We call this era the cosmic dawn, the moment when the universe lit its first fires. But how that transformation began remains one of astronomy's greatest mysteries. How did the first stars ignite in a universe that contained no heavy elements, no dust, no carbon, no oxygen, only the simplest atoms? The physics is known in part, but the details, the moment when darkness bloomed into light, are still hidden. Astronomers believe that the first stars, called population 3 stars, formed from immense clouds of hydrogen and helium that collapsed under their own gravity. Without the metals that help cool modern gas clouds, these early giants grew far larger than any stars we see today, perhaps hundreds of times the mass of our Sunday. They burned hot and bright, pouring ultraviolet light into the surrounding void, reionizing the universe and ending the cosmic dark ages. But none of these stars have ever been seen. Every one of them lived fast and died violently, exploding in titanic supernovae just a few million years after birth. They left behind no direct trace, only whispers in the chemistry of later generations of stars. The elements forged in their cores, carbon, oxygen, iron, and everything we are made of, were scattered across space, seeding the raw materials for planets, oceans, and eventually, life. In a sense, we are the descendants of those first stars. Every atom of our bodies was once part of their fire. When we breathe, we are carrying the ashes of cosmic ancestors, the echo of that first light still glowing within us. The mystery, however, remains unsolved. If the early universe contained only simple gas, how did the first dense knots of matter form at all? What triggered the collapse that led to the birth of stars? Was it the subtle gravity of dark matter, drawing invisible halos that gathered gas into clumps? Or was it turbulence, ripples from the Big Bang itself, shaping pockets of higher density where the first stars could take form? Simulations give us clues, but the answers lie buried in distances so vast and times so ancient that even our most powerful telescopes can barely glimpse them. The James Webb Space Telescope is now peering back toward that lost dawn of creation. Each of its infrared images is a time machine reaching across billions of years to catch the faintest glimmer from the first galaxies. Already, it has revealed surprising truths. Galaxies forming earlier and faster than models predicted, massive clusters existing when the universe was still in its infancy. It suggests that star formation began almost as soon as the universe cooled enough to allow it, as though creation itself was eager to begin. But there is something haunting about those first lights. They were never meant to last. The giants of the early cosmos lived brief, furious lives, shaping the conditions for everything that followed, and then vanishing completely. In their death throes, they may have given birth to the first black holes, the seeds of the supermassive giants that now sit at the centers of galaxies. Through destruction, they created the architecture of everything to come. When you look up at the night sky, every star you see is a descendant of those ancient fires. The Milky Way itself was sculpted from their ashes. The light that reaches your eyes tonight is the continuation of a story that began in darkness and ended in brilliance. And though we may never witness a population 3 star directly, we live in their legacy. The atoms in our blood were once fused in the hearts of forgotten suns. Their energy became the spark for galaxies, for chemistry, for life. The universe remembers their fire in every photon of light and in every heartbeat that still burns across time. Perhaps that is why starlight feels so familiar, because it is where we came from. The first stars were not only the beginning of the universe's illumination, but also the beginning of awareness itself. Their deaths wrote the elements that would one day look back at the sky and wonder how the darkness learned to shine. Across the universe, there are signals that appear for a heartbeat, bright flashes of radio energy that come and go without warning. They last only a few milliseconds, yet in that instant, each releases as much energy as the sun does in an entire year. These are fast radio bursts, or FRBs, cosmic whispers that have become one of the strangest mysteries in modern astronomy. The first FRB was discovered in 2007, a burst so brief it was nearly dismissed as noise. But soon, more followed. Flashes scattered across the sky, each coming from a different, distant corner of the cosmos. Some appear only once, never to repeat. Others pulse again and again, as though some unknown hand is knocking on the door of reality. No one knows what causes them. Theories range from the natural to the extraordinary. Many scientists believe they come from magnetars, highly magnetized neutron stars left behind after supernova explosions. These stellar corpses can twist and snap their magnetic fields, releasing bursts of energy so intense that they ripple across galaxies as radio waves. Others suggest that FRBs might result from collisions, neutron stars merging, black holes devouring companions, or matter falling violently into gravitational wells. Each explanation fits some of the data, but not all. The repeating bursts complicate the story. If an FRB came from a single cataclysmic event, it should not happen again. And yet, some sources flicker repeatedly with rhythms that almost seem deliberate, though likely only by coincidence. They speak in patterns too precise to ignore, but too inconsistent to decode. In 2020, astronomers traced one such burst to a magnetar in our own galaxy, proving that at least some FRBs are natural. Still, many remain unexplained, coming from billions of light-years away. Voices from an age before Earth even existed. To detect them, scientists use giant radio telescopes, arrays stretching across mountains and deserts, listening to the static of the universe. Each discovery is like catching lightning in a bottle, a sudden, sharp spike in data that vanishes almost before it can be recorded. When computers flag a burst, astronomers race to trace its origin, to pinpoint which galaxy, which cluster of stars, sent this fleeting message across cosmic time. But as they study these strange outbursts, they find that FRBs can pass through the invisible structure of the universe. Like probes through fog, their signals stretch and scatter, as they travel through gas and plasma between galaxies. By analyzing those distortions, scientists can map the distribution of matter in the vast cosmic web. Even the elusive baryons and filaments that have long escaped direct observation. Each FRB, though brief, becomes a tool for measuring the unseen. A flash of data carrying the fingerprints of everything it passes through. And yet, there is something poetic about them. Imagine a pulse of radio energy born in the collapse of a distant star, racing through billions of light-years of space, past galaxies and nebulae, past dark matter and dust, until it brushes against our tiny world and vanishes into an antenna for a fraction of a second. A single cosmic heartbeat echoing through eternity. A message we can hear but not yet read. Some dreamers have wondered if FRBs could be signals, not from stars, but from minds. Artificial transmissions sent by civilizations far older than ours. Most scientists doubt this explanation, but it lingers, not because it is likely, but because it reminds us how much we still don't know. The universe has been broadcasting long before we were here to listen. Perhaps we are just beginning to tune in. Even if the truth is purely natural, FRBs remind us how dynamic the cosmos truly is. It is not a silent, still expanse, but a living sea of motion and energy, alive with bursts and waves and echoes of creation. The same universe that forged the first stars still crackles with electricity, still sings in radio tones across unimaginable distances. So, when an observatory catches that brief spike of light, that sudden note from the farthest dark, it is as if the cosmos itself has spoken. A single syllable in a language older than time, and though we may not yet understand it, we listen again and again, because somewhere within those fleeting flashes might lie a story, a rhythm, a pattern of meaning written in the static of eternity. Perhaps one day, and our patience longer, we'll begin to understand what the universe is saying. Until then, we wait in the quiet between bursts, ears pressed to the fabric of space, listening for the next heartbeat of the cosmos. Between the bright filaments of galaxies lies the deepest silence. Immense cosmic voids, vast regions of space almost completely empty of matter. They stretch for hundreds of millions of light-years, so large that entire clusters of galaxies could drift through them without ever meeting another. In the great web of the universe, these voids are the dark spaces between the luminous threads. And yet, they may hold clues to how everything we see came to be. When astronomers map the universe on the largest scales, it looks like a three-dimensional web. Galaxies form along filaments and walls, while between them yawns an intricate network of emptiness. This cosmic architecture, the large-scale structure of the universe, was shaped by gravity pulling matter together and by dark energy pushing space apart. But the exact balance that formed the pattern we see remains one of the great puzzles of cosmology. Voids seem empty, but they are not truly nothing. They contain a thin haze of gas, a few scattered galaxies, and the faint glow of dark matter we cannot see. In these places, the universe expands faster than average, stretched by the repulsive pressure of dark energy. The edges of voids act like cosmic borders, where matter gathers into filaments, stars ignite, and galaxies cluster together. In a way, the voids give the cosmos its structure. By defining where things aren't, scientists use these voids as laboratories for testing gravity itself. Because there is so little matter inside them, subtle effects become visible. Minute distortions of light, variations in the rate of cosmic expansion, and patterns that reveal how dark energy behaves. By studying the shapes and sizes of voids, astronomers can measure how the universe has evolved over billions of years. The growth of emptiness tells us as much about the cosmos as the light of the galaxies themselves. And yet, some of these voids are bigger than expected, too large to fit neatly within standard cosmological models. The so-called Bootes void, for instance, spans over 300 million light-years and contains almost nothing inside. Why should such immense gaps exist at all? Were they carved by the uneven expansion of space, or are they relics of primordial fluctuations from the earliest moments after the Big Bang? Perhaps the distribution of dark matter, unseen but powerful, shaped them in ways we still don't understand. In their emptiness, the voids become mirrors. They reflect not light, but meaning. To stare into one is to confront the loneliness of the cosmos, a reminder that most of the universe is not filled with stars, but with nothing at all. Even galaxies, planets, and life are rare interruptions in an ocean of emptiness. Yet, paradoxically, it is that emptiness that allows structure to exist. If the universe were perfectly uniform, nothing could ever form. The voids and the clusters, the dark and the bright, depend on one another, each giving the other its shape. Some physicists believe these cosmic gaps could help us understand the mysterious force of dark energy itself. In regions of low density, where gravity's pull is weakest, the expansion of space seems to accelerate more freely. By comparing how voids grow over time, we can learn how dark energy changes, whether it is constant or evolving, a quiet pressure or a restless tide. In this sense, every empty space becomes a measuring stick for the fate of the universe. But beyond the science, there's something profoundly human in the idea of the void. It speaks to the silence that surrounds all creation, to the spaces between things where potential gathers before form arises. Just as a pause gives meaning to music, the cosmic voids give rhythm to existence. They are the rests between notes in the symphony of the cosmos, and even within them, there is movement. Tiny galaxies drift like lanterns across vast black seas. Streams of dark matter flow unseen, linking distant edges of the cosmic web. Gravity whispers across incomprehensible distances, pulling and stretching the emptiness itself. Even where there is almost nothing, the universe is still alive. Perhaps the voids are not empty at all, but filled with the hum of invisible fields, the fabric of space-time vibrating softly, carrying the memory of all that was and all that will be. To look into that silence is to glimpse the soul of the cosmos, an ocean of stillness upon which every star, every world, and every moment is just a brief ripple. So when you look at the night sky, remember that the light you see is surrounded by far greater darkness. But that darkness is not absence. It is the background that makes everything possible, the canvas on which creation paints its fleeting shapes. The universe breathes in light and breathes out emptiness, and both are needed for it to exist at all. Every story has an ending, even the universe. But how that ending will come remains uncertain. Will everything fade into eternal darkness, or will the cosmos collapse back into fire? Scientists have imagined many possible fates for reality, each one shaped by the delicate balance between gravity and dark energy, between attraction and expansion, between creation and silence. Right now, the evidence suggests that the universe is expanding, and that this expansion is speeding up. Galaxies are drifting farther apart, their light stretching into longer and redder wavelengths, as space itself grows between them. If this acceleration continues forever, the cosmos will head toward a slow, cold extinction, a destiny known as the heat death. In this scenario, trillions of years from now, stars will exhaust their fuel and fade. Galaxies will dim to faint glows, their last suns cooling into black dwarfs. Over unimaginable spans of time, even those remnants will vanish, leaving only dead matter and radiation, spreading ever thinner through an endless void. The temperature of space will fall close to absolute zero, and the universe will become a quiet ocean of entropy, uniform, lifeless, still. In that frozen eternity, time itself may lose meaning, for nothing will remain to change. But this is only one possibility. If dark energy behaves differently than we think, the story could end in a far more violent way. If its strength increases over time, the expansion of the universe will accelerate without limit, ripping apart galaxies, then stars, then planets, and finally even the atoms themselves. This catastrophic future is called the Big Rip. It would be the universe's final act, a crescendo of disintegration, as space-time itself tears into fragments. There is another path, however, one that leads not to destruction, but renewal. If dark energy someday weakens or reverses, gravity could regain control. The expansion would slow, then stop, and the universe would begin to contract. Galaxies would draw together, stars would collide, and matter would heat to unimaginable temperatures. Eventually, everything would collapse into a single, blinding singularity, a mirror image of the Big Bang. This is the Big Crunch, a universe ending where it began, perhaps to start again in another cycle of birth and death. Some cosmologists imagine an even stranger fate, a perpetual rebirth called the Big Bounce. In this model, the universe expands, collapses, and expands again, over and over, without end. Each cycle wipes away the traces of the previous one, but leaves subtle imprints in the background radiation, cosmic echoes of earlier worlds. If this is true, our universe may not be the first, nor the last, but one of an infinite series, each one breathing life into the next. There are even more speculative endings, quantum fluctuations. The random tremors of space-time could someday trigger a sudden change in the laws of physics, a transformation known as vacuum decay. If the vacuum we live in is only a temporary state, a more stable one could appear, expanding outward at the speed of light, erasing everything in its path without warning. It would happen so quickly that we would never feel a thing. In an instant, reality itself would rewrite its code. Each of these endings sounds apocalyptic, but they also reveal something profound. The universe is not static. It has a history, a pulse, a rhythm of transformation that connects beginning to end. The same laws that gave birth to galaxies and life also determine how everything will fade away. We are part of that story, a moment in the cosmic arc between creation and completion. What makes the question so haunting is that the universe's fate is also our own. The atoms in our bodies, the air we breathe, the warmth we feel, all will one day dissolve back into the larger silence. And yet, that silence is not loss. It is continuation. Just as stars die and scatter their elements into new forms, perhaps the universe itself will do the same, ending only to begin again. For now, we exist in the middle chapters, in the age of light, when stars still burn and galaxies still spin. We can look up at the sky and see both the universe's past and its possible future, written in the faint glow of distant suns. The cosmos has not yet chosen its ending, and maybe it never will. Perhaps the story of existence is not about how it ends, but how it continues to change. So as you drift to sleep beneath the stars, remember this: you are living inside a universe still in motion, a universe still deciding its destiny. And whether it fades into cold, collapses into flame, or breathes anew in an eternal rhythm, you are part of that grand unfolding, a moment of awareness in the infinite life of the cosmos. Long before there were minds to ask questions or eyes to look at the stars, something extraordinary happened on a small, blue planet. Out of lifeless chemistry from water, minerals, and molecules, something began to move, to copy itself, to change. From that first spark, everything we call life emerged. Yet, for all our progress, we still don't know how it began. The origin of life remains one of science's deepest mysteries. We can trace evolution from simple organisms to complex beings, but the moment when non-living matter crossed the threshold into biology is still hidden in the deep past. Somewhere between geology and chemistry, something learned to remember. A molecule became a message, and the universe, for the first time, began to know itself. Most scientists believe life began more than 3.5 billion years ago, shortly after Earth cooled and oceans formed. Our planet, once a molten wilderness, became a world of water, storms, and lightning, an enormous laboratory filled with energy and possibility. In this environment, simple molecules collided and combined. Out of these endless chemical dances, chains of carbon and hydrogen formed more complex structures: amino acids, lipids, and nucleotides, the building blocks of every living thing. But how did those ingredients come together into something that could reproduce? That question still defies certainty. One leading idea is the RNA world hypothesis. RNA, a cousin of DNA, can both store information and act as a catalyst for chemical reactions. Perhaps the first living systems were networks of self-replicating RNA molecules, tiny loops of code that made imperfect copies of themselves, and through those errors, over time, they could have built the complexity that eventually gave rise to DNA and the genetic machinery of life. Others imagine that life began in the depths of the ocean, near hydrothermal vents, where superheated water mixed with minerals from the planet's crust. These vents created natural chemical gradients, a source of energy and structure, tiny compartments where reactions could occur again and again, until something astonishing emerged, a molecule that could copy itself. That was the beginning of evolution, and perhaps of memory. Still, other theories reach beyond Earth. Some scientists believe the seeds of life may have come from space, that meteorites and comets carried organic molecules, formed in the icy clouds between stars. We have found amino acids in comets and complex organics drifting in interstellar dust. Perhaps life did not begin here at all, but was delivered, already in potential, by the stars themselves. This idea, known as panspermia, turns every world into a possible cradle of life. Yet, no single theory answers everything. We can replicate fragments of the process in laboratories, creating the ingredients of life under simulated early Earth conditions. But no experiment has yet produced a self-sustaining, evolving system, a true spark of life from scratch. It is as if nature guards this secret, allowing us to glimpse the edges of the puzzle, but not its center. What makes the mystery even more profound is that we don't know how common this miracle might be. If life arose naturally on Earth, then perhaps it could arise elsewhere, wherever the same conditions exist. If it required an almost impossible chain of events, then we might be alone. Either answer is staggering. To be one of countless living worlds, or the only one, both fill the heart with wonder and humility. Life's emergence also raises another question. Did it begin once, or many times? Was there one single ancestor from which all life descends, our universal parent cell, the so-called Luca last universal common ancestor? Or did multiple origins flicker into being before merging into one lineage? DNA connects all known life, but perhaps there were others, forms that failed, faded, and left no trace but possibility. The birth of life was not the creation of perfection, but the creation of persistence, something that could adapt, endure, and remember enough to continue. From those humble beginnings came everything: trees, oceans, wings, thoughts, and dreams. The story of life is the story of matter awakening, and of atoms learning to arrange themselves into meaning. Even now, scientists search for that first transition, not just to explain our past, but to understand the boundary between the living and the non-living. Because somewhere in that boundary lies the secret of what we are. We are walking chemistry, ancient molecules refined by time, carrying echoes of an origin so profound that even science speaks of it in whispers. So the next time you look at your hands, remember that the elements within them were once dust, then water, then the pulse of something that learned to grow. Life is not a single event, but a process still unfolding, a question still being asked by the universe itself. And perhaps, somewhere, in another world, another ocean is stirring, asking the same question again. How does something without life learn to live? Every living thing on Earth, every plant, every animal, every person shares the same fundamental code: 4 simple letters, A, T, C, and G, arranged in endless combinations, carrying the instructions for all of life. This is DNA, the molecule that remembers how to build everything that exists. It is elegant, universal, and unimaginably ancient, and yet, for all we know about it, we still do not understand why life chose this particular form. DNA's structure is deceptively simple: 2 spiraling strands forming a double helix, bound together by pairs of bases that fit like puzzle pieces. A connects to T, C connects to G. From these pairings arise all diversity, from the color of a butterfly's wings to the consciousness that wonders how wings came to be. But why this molecule? Why this shape? Why this precise alphabet of 4? Chemistry allows for countless alternatives, and yet life, from bacteria to whales, chose only one. Some scientists believe DNA's dominance was inevitable, that it is the most stable, efficient way to store and copy information in a chemical medium. Its double helix protects the code within, and its complementarity allows replication with remarkable accuracy. Others suspect that DNA was not the first. Before it, there may have been another system, perhaps based on RNA, which is simpler and can both store data and catalyze reactions. In that case, DNA may have taken over later, chosen by evolution for its endurance. But that only moves the mystery one step earlier. Why RNA, or any molecule at all, should have learned to encode meaning. The transition from chemistry to code was one of the most miraculous events in the history of the universe. At some point, random sequences of molecules began to carry instructions. Those that copied themselves most reliably survived. Over time, the code grew longer, its grammar more complex, until it could describe not only molecules, but minds. We are the descendants of that first syntax, the living continuation of a molecular poem that began billions of years ago. DNA does not merely store information, it also remembers change. Every mutation, every adaptation, every response to survival is written into its spiral. The human genome is a library of history, a record of every trial and triumph life has endured. There are genes in your body that trace back to the earliest bacteria. There are ancient viruses hidden in your DNA, remnants of infections long extinct. And yet, all of it still works together, a symphony of inherited memory. The more we learn about DNA, the stranger it becomes. We have discovered that it can fold into alternative shapes, that it can repair itself, and even that it may respond to patterns of energy within the cell. It behaves not like a simple chemical, but like a dynamic network, storing, retrieving, and editing data in ways we are only beginning to comprehend. Some researchers even describe it as a kind of biological computer, one that uses molecules instead of silicon. Each strand carries 3 billion letters of code, and yet it fits inside a single nucleus, so small you could fit 1 million of them on the head of a pin. There is also the mystery of chirality, the handedness of molecules. DNA twists only one way, always to the right. The sugars and amino acids of life all share the same orientation. Chemically, the opposite versions could exist, but in all of biology, they do not. Why did life choose one direction and not the other? It may have been chance, a small asymmetry at the beginning that became universal. Or it may reveal something deeper, a subtle bias in the laws of physics that favors life's particular geometry. When you think about it, DNA is the universe writing itself into form. Atoms born in stars combine into molecules, which combine into living systems, which in turn gain the power to look back and study themselves. We are chemistry becoming conscious, and every cell in your body carries the complete story, not just of you, but of all life on Earth. It's humbling to realize that this code, so intricate and perfect, could have arisen by chance. Yet, in a universe of infinite possibilities, perhaps inevitability hides within randomness. Given enough time, matter organizes itself toward complexity, toward memory, toward meaning. Perhaps the laws of nature make life not an accident, but an expected consequence, a natural expression of the universe's desire to know itself. So the next time you see a leaf or a bird in flight, or your own reflection in the mirror, remember that what you are seeing is the universe reading its own instructions. A pattern written in molecules billions of years ago, still unfolding in every breath you take. The double helix in your cells is not just a structure, it is a story. One written in 4 letters, told across all of time, and still being written in you right now. Every night, the boundary between reality and imagination dissolves. The lights dim, the world fades, and the mind begins to create its own landscapes. We drift into dreams, vast, silent stories that unfold behind closed eyes. In them, we can fly, fall, or revisit forgotten faces. We can relive the past or touch impossible futures. And yet, for all the familiarity of dreaming, no one truly knows why it happens. Science can describe when we dream, but not why. During the phase known as REM sleep rapid eye movement, the brain becomes astonishingly active. Neurons fire as though awake, images flicker across the visual cortex, and the limbic system, where emotion lives, flares to life. Meanwhile, the logic centers of the prefrontal cortex grow quiet. Reason fades, boundaries blur, and narrative takes over. The brain becomes a storyteller. Some scientists believe dreams serve a biological purpose. They may help organize memory, replaying fragments of the day to strengthen useful connections, and discard the rest. Others think dreams are emotional rehearsals, safe spaces for the mind to process fear, grief, or desire. A nightmare may simply be the brain practicing how to survive, but none of these explanations fully capture the strangeness and depth of what we experience when we dream. For centuries, philosophers and mystics have treated dreams as messages from the unconscious, windows into hidden thoughts or parallel realities. Freud saw them as coded expressions of desire. Jung called them bridges to a collective mind, a shared realm of symbols older than humanity itself. Modern neuroscience offers different answers, but even it cannot explain the vivid creativity that arises from sleep. Where do these images come from? Why do they feel so real while we are inside them and vanish like mist when we wake? Dreams are also paradoxes of perception. While we sleep, the brain is disconnected from the outside world, yet it generates entire worlds within itself. It fills them with sound, light, touch, even pain, crafted entirely from memory and imagination. During lucid dreams, some people even realize they are dreaming and can shape those worlds at will. In that moment, they become both creator and observer, conscious within the unconscious, a glimpse of awareness inside illusion. And then there is the mystery of why we must sleep at all. Sleep is dangerous, especially in nature. A sleeping creature is vulnerable, yet every animal on Earth does it, from insects to whales. Some sleep while half their brain stays awake, others drift in motion, gliding through currents or air. Sleep is as vital as breathing or eating. Without it, the mind deteriorates, memory fractures, and reality itself begins to blur. The question is not only what sleep does, but why evolution built it into the very fabric of life. Perhaps sleep is more than rest. Perhaps it is the body's way of stepping aside, so the mind can perform its deepest work, repairing, integrating, dreaming. While we lie motionless, billions of neural connections rewire themselves, memories replay, emotions untangle, and consciousness resets for another day. Dreaming may be how the universe within us restores its order, a nightly act of creation. There is also the strange overlap between dreaming and creativity. Throughout history, dreams have given birth to inventions, music, and discoveries. The structure of the benzene molecule, the melody of Yesterday, the plot of Frankenstein, all came from dreams. It's as though the sleeping mind holds doors that the waking mind cannot open. When logic sleeps, imagination wakes. Yet, for all their wonder, dreams are fragile. They dissolve the moment we try to grasp them. You may wake with the memory of a vivid world, its colors, its textures, its impossible logic, but within minutes it fades, leaving only the feeling that something extraordinary just occurred. Perhaps that's the point. Dreams are not meant to last. They are temporary bridges between the known and the unknown, the conscious and the infinite. The mystery of dreaming reminds us that our minds are larger than we realize. Inside every skull, is a universe capable of generating galaxies of thought, of bending time and space into stories each night. And in that darkness, the brain rehearses what it means to exist, to fear, to love, to lose. Dreams are the echo of consciousness learning to imagine itself. So when you close your eyes tonight, know that you are entering the oldest theater in existence, a space without walls, where the universe performs for itself in endless variations. You are both audience and author, watching reality being rewritten from within. And though you may not remember the script when you wake, its traces will remain in your emotions, your decisions, and the quiet rhythm of your thoughts. Every night, the mind creates worlds, and every morning, it lets them go. Dreams are reminders that even in rest, we are still exploring. Not the stars this time, but the infinite cosmos inside. What is consciousness? It is the most intimate thing we know, and the greatest mystery we face. Every thought, every feeling, every memory you have ever had exists within this fragile phenomenon. You can see stars a billion light years away, but you cannot see consciousness itself. You can measure the brain's activity, but not the spark that turns that activity into experience. Consciousness is what makes you you. It is the quiet witness behind your thoughts, the awareness that says, I am, and yet, science still cannot explain how it arises. We know the brain's structure in astonishing detail. Billions of neurons linked by trillions of synapses, exchanging signals like electrical whispers. We can observe which areas activate when you dream, when you speak, when you fall in love or remember the past, but none of that tells us why there is something it feels like to be alive. Why should matter, arranged in a certain way, suddenly awaken and begin to experience itself? This puzzle is known as the hard problem of consciousness. It was named by philosopher David Chalmers, who distinguished between the easy problems, like how we process information or control movement, and the truly difficult one, why any of that should come with inner experience at all. Why should a collection of cells generate the sensation of color, or the ache of sorrow, or the joy of music? From the outside, the brain is a machine of chemistry and electricity. From the inside, it feels like a life. Some scientists believe consciousness is an emergent property, that when information flows through a system complex enough, awareness naturally appears. In this view, consciousness is not separate from matter, but a pattern of matter in motion, like a song played on the instrument of the brain. Others propose that consciousness may be fundamental, a basic property of the universe, like space, time, or gravity. This idea, called panpsychism, suggests that even the smallest particles contain tiny flickers of experience, and that the human mind is simply a grand symphony of those microcosmic notes combined. Then there are theories of integrated information, mathematical models that attempt to quantify awareness itself. They argue that consciousness depends on how information connects, not on what the information is. A system with enough integration and feedback begins to generate a self, a unified field of awareness that cannot be reduced to its parts. In that sense, consciousness is not in the brain, but the pattern of how the brain holds itself together. Despite all our progress, we cannot yet explain why one brain state corresponds to sadness and another to awe. We can stimulate the visual cortex and make someone see flashes of light, but we cannot capture what that light feels like. We can describe neurons firing in harmony. When a person listens to music, but not the sensation of beauty that rises within them. The first-person world, the inner experience of being, remains unreachable to third-person science. Some researchers look for clues in altered states of mind, in dreams, meditation, or near-death experiences. They find that consciousness is not a single thing, but a spectrum expanding, contracting, and changing its texture depending on what the brain is doing. Others study how awareness can disappear under anesthesia, then return as if nothing happened, as though the universe itself had paused and resumed. What happens to the self in those moments? Does it vanish entirely, or does it simply lose the ability to notice itself? And then there is the question of artificial consciousness. Could a machine ever become aware? If we build a computer with circuits mimicking the human brain, would it one day wake up? Or is there something uniquely biological about consciousness, something that cannot be simulated? If machines ever claim to feel, how will we know if they truly do? The question is not only scientific, but deeply philosophical and perhaps ethical, because to understand consciousness is to understand the value of experience itself. No other mystery cuts closer to who we are. Without consciousness, there is no meaning, no love, no memory, no world. It is the screen on which everything appears, and the one thing that never appears on the screen. We spend our lives looking outward, yet consciousness is what looks. It is both the seeker and the sought, the question and the answer, the observer and the universe observing itself. Perhaps that is why it feels sacred, even to those who do not use that word, because in every moment of awareness, in every breath, every thought, every flicker of being, the cosmos becomes alive through you. Your mind is not separate from the universe. It is the universe remembering itself for a brief and shining instant. So when you close your eyes and awareness settles into silence, know that what you feel as you may be the universe's oldest secret, the light that turns existence into experience. And whether it arises from atoms or eternity, consciousness remains the most beautiful mystery of all. Memory is the thread that stitches time together. Without it, every moment would vanish as quickly as it arrived, leaving no story, no self, no sense of continuity. It is because we remember that we can learn, love, and dream, and yet remains one of the most elusive functions of the mind. Where exactly do memories live, and how do fleeting experiences become the architecture of identity? Neuroscience has mapped the brain in stunning detail, but the mechanics of memory remain mysterious. We know that the hippocampus acts as a kind of index, organizing experiences and sending them for long-term storage across different regions of the cortex. But a memory is not a single file stored in one place. It is a pattern of activation, a constellation of neurons firing together in rhythm. To recall a moment is to recreate it, to reassemble its pattern from fragments scattered across the brain. When you remember something, your mind doesn't simply open a drawer and retrieve it. It rebuilds it, piece by piece. The smell of rain, the sound of laughter, the warmth of a hand. Each sensation comes from a different part of the brain, stitched together by the act of remembering. That is why memory is so powerful, and also why it is so fragile. Each time we recall, we change it slightly. Every memory you hold has been rewritten many times, reshaped by emotion, colored by the present. What we call the past is never quite what it was. Scientists have discovered that memory is not static, but alive. Neurons form new connections even as we sleep, and old ones fade away. When we learn, the brain physically rewires itself, a process called neuroplasticity. Every thought leaves a trace, every habit a pathway. Over time, these patterns become the roads of the mind, the routes by which identity travels. And yet, for all its sophistication, memory can vanish suddenly. Diseases like Alzheimer's erode the neural structures that hold our stories. Faces blur, names fade, and the self begins to dissolve. To watch memory slip away is to see a person slowly untether from time. It raises a painful question. If our memories define us, who are we when they are gone? The truth may be gentler than it seems. Even when memory fades, something deeper remains. The emotional trace of connection, the body's quiet remembrance of love. A person who no longer knows your name may still respond to your voice, to the comfort of touch, to the rhythm of a familiar song. It suggests that memory is not just stored in the mind, but in the whole being, woven through every sense, every heartbeat. There are also memories we never consciously record, the implicit ones. They live in our instincts and habits, guiding our reactions without our awareness. They are the reason we can ride a bike after years away, or feel uneasy in a place that once held danger. These silent memories remind us that the brain does more remembering than we realize. And then there are false memories, recollections of events that never happened. Experiments show that the human mind can be convinced to remember entire scenes that are complete inventions. Memory, it seems, is not a camera, but a storyteller, and sometimes it improvises. This creative aspect of remembering might be the same ability that allows us to imagine, to create art, to dream of futures that do not yet exist. To remember is, in part, to invent. Even more mysterious is why certain moments remain vivid forever, while others disappear within days. Emotion plays a powerful role. A single moment of joy or trauma can imprint itself so deeply that decades later it can still quicken the heart. Adrenaline, dopamine, and other neurochemicals strengthen the connections formed in those intense moments, etching them into the brain's circuitry. Our memories are not a neutral record. They are shaped by what matters to us. In that way, memory is less about the past and more about meaning. Perhaps that is why memories can move us so deeply, because each one is a bridge between who we were and who we are becoming. When you remember, you collapse time, letting the past live again in the present. It is a quiet kind of time travel, a miracle we perform every day without noticing. So, when you close your eyes and recall a moment, a childhood afternoon, a face you loved, the sound of distant rain, you are touching the continuity of your own existence. You are proving that something within you has endured every change. Memories may fade, but the capacity to remember, to feel the echo of what once was, is eternal. Memory is not just the story of your life. It is your life, constantly rewritten, constantly renewed. And perhaps, in the deepest sense, to be alive at all is to remember. Among all the mysteries of existence, one stands closest to the heart. We can explain the stars, but we still do not fully understand why we love, why we care for others, why we feel joy and sorrow intertwined in the same breath. Love is both biology and poetry, a force that defies easy definition, part chemistry, part consciousness, part eternity. At the simplest level, love begins in the body. It is written in the brain's circuitry, guided by chemicals like dopamine, oxytocin, and serotonin. When you hold someone close, your brain floods with these molecules, signals of trust, comfort, and connection. They calm your heartbeat, lower your stress, and remind your body that it belongs somewhere. In evolutionary terms, love is a survival mechanism, a bond that keeps parents near their children, partners near each other, and communities strong enough to endure. It is nature's way of ensuring that life continues, but biology alone cannot capture its depth. Because love also exists in forms that defy utility. The love that persists after loss, the love that seeks nothing in return, the love that extends beyond species or strangers. These expressions of the heart suggest that love is not merely instinct, but awareness, a recognition of connection that runs deeper than reason. Neuroscientists can trace love's pathways through the brain, lighting up regions tied to reward, empathy, and attachment. But no scan can show what love feels like. That warmth when you see a familiar smile, that ache when you watch someone walk away. The invisible gravity that draws two lives together from opposite corners of the world. Love, like consciousness itself, may be less a process than a presence, the universe becoming aware of its own unity. Poets have always known this. Long before science, humans sang of love as something sacred, a force that shapes not only hearts but destinies. Across cultures and centuries, the language changes, but the essence remains the same. Love binds what is separate. It teaches empathy, forgiveness, and wonder. It is the bridge that connects us not just to each other, but to life itself. What makes love even more mysterious is its dual nature, the way it can bring both joy and pain. To love deeply is to risk heartbreak, yet without it, life feels hollow. Love's power lies in that paradox. It opens us to vulnerability, to loss, and yet also to transcendence. Every act of love is a small defiance against entropy, a refusal to let the universe drift into isolation. In a cosmos tending toward disorder, love is the one force that builds harmony. Science, for all its clarity, still cannot say why love exists. It can show us the patterns, the hormones, the brain waves, but not the meaning. Perhaps meaning itself is love, the sense that something matters. Without love, knowledge would be sterile, truth would be cold, and consciousness would have no purpose. Love gives existence a reason to continue. There is also the mystery of where love goes. When a person dies, when years separate two hearts, when time erases the details, why does the feeling remain? Why can a song or a scent bring tears decades later? Love seems to ignore the boundaries of time. It lingers, echoing across years and distance, as though once formed, it cannot be destroyed. In that way, love behaves like energy. It changes form, but it never vanishes, even at the end of life. When memories fade and identities dissolve, the capacity for love endures. A mother may forget her child's name, but still reach out in tenderness. A person might lose every memory, but smile at a familiar touch. Love resides deeper than memory, deeper than thought, perhaps deeper than life itself. If we look closely enough, we see love everywhere. In the gravity that binds atoms, in the cooperation of cells, and the patterns of nature that favor connection over chaos. Maybe love is not only a human feeling, but a principle of the universe, the tendency of things to come together, to create more than the sum of their parts. It may be the cosmic mirror of gravity pulling hearts instead of planets. And so, love remains both the simplest truth and the greatest mystery. We cannot measure it, yet it shapes our every action. We cannot define it, yet it defines us. We are born through love, we live in search of it, and in the end, we return to it. Perhaps that is all existence really is, the universe learning. Again and again, how to love itself through the eyes of those who remember. And so, we return to where we began, to mystery itself. From the birth of stars to the whisper of DNA, from the silence of black holes to the voice that asks why, we have drifted through the questions that define what it means to exist. Science has carried us far. It has shown us the age of the cosmos, the structure of atoms, the rhythm of life. But beyond every answer waits another horizon. Each discovery is a doorway, not an ending. Perhaps that is the secret. That wonder is infinite. The universe does not owe us clarity, yet it gives us beauty. The shimmer of galaxies, the warmth of a touch, the awareness that sees itself reflected in starlight. We are fragments of that light, brief but luminous, alive for a moment in the vast conversation of time. As you rest tonight, let the unknown comfort you. You do not need to solve it. You only need to feel it. The quiet pulse of being, the music between atoms, the stillness beneath thought. You are part of it all. You always have been, because the cosmos is not separate from you. It dreams through you. It breathes through you. And in every heartbeat, it remembers itself. The questions will never end. And that is the most beautiful truth of all. Good night, and see you in the next video.